So let's talk about the KSP. So now we are going to start talking about solubility. So switching gears and talking about ionic compounds that are soluble, insoluble, or slightly soluble. So KSP is the solubility product constant, and this is when dealing with ionic compounds that are insoluble or slightly soluble. So remember, we often will refer to ionic compounds as salts. So if you hear that, it is just the same thing. So soluble means that it dissolves, and we're going to be talking about water as the solvent, and that would result in an aqueous solution. If something dissolves in liquid water, that would make it an aqueous solution if a salt dissolved in liquid water. Insoluble means it does not dissolve. That means it would be a solid. Sometimes you might see this called a precipitate, PPT, meaning it has fallen out of solution. Sometimes when you take two liquids, you put them together and they form an insoluble solid, you'll see a precipitate form, and that's just another word for a solid. So remember, when we talk about dissolve, the word dissolve, we really just mean ionize, dissociate. So dissolve is synonymous with break apart, dissociate, ionize. All of those mean the same thing. So we have quite a list of equilibria constants that we've talked about. So there was the Kc, and that C was concentration. And we've had the Kp, and that was the equilibrium constant with respect to pressure. And then we had the Ka, which was for acids, and we've had the Kb for bases, and we've had the Kw for water, and now we have the Ksp, which is for solubility. So we're talking about equilibria and solubility. So the way we write the Ksp is the same way that we write all of the other equilibria constants. Ksp is the relationship of the concentration of the products to the concentration of the reactants. And remember, coefficients become exponents, and pure substances like solids and liquids are excluded. I say excluded, sometimes you'll see them replaced with a 1 or replaced with a 1, the number 1, just as kind of a placeholder, just in case you happen to see it written that way other places. So let's just write the generic formula for solubility, and it is this: Mx, where this would be an ionic compound, a solid ionic compound. It's going to break apart and form the cation, which would be aqueous. Remember this +1 because it is a positively charged cation, which comes first in the compound. There is no element M or element X, which is why we use these just as kind of generic to represent anything, plus X minus, which is also aqueous. So the Ksp, so this is over here reactant, and over here product. So if you were to write the Ksp equals the concentration of the products over the concentration of the reactants. But the reactants are solids, so it is excluded from equilibrium. So you don't see it in the equilibrium of the KSP. You just see KSP equals the concentration of the two ions. That is what we're using to determine the KSP. So the KSP tells us how much of this salt will ionize because it's the product of these two ions. The more ions break apart, the higher the KSP will be. So the KSP tells us how much of the salt will ionize or break apart into its ions. So the higher the KSP, the more ions produced. The more of the salt that will break apart. Another way to say this is as the KSP increases, the solubility increases. So when we talk about solubility, having high solubility means more of the salt would have broken apart, and to have low solubility means less of the salt would break apart. So the KSP is really a ratio of ionized soluble ions to unionized unsoluble ions. So it's telling us how much of this salt breaks apart. We're going to do a lot of examples of these. Something else that is worth pointing out is that solubility can be expressed in a few different ways. It can be expressed in molar solubility, which is moles per liter. That is pretty standard. It can also be expressed in just regular solubility, which is grams per liter. So if you see solubility in terms of grams per liter, you would need the molar mass to convert moles to grams to express a solubility in grams per liter instead of moles per liter. So we'll get into some calculations and see some examples of using KSP when talking about solubility, but this is kind of the background that we need to know before we get into that.